Hey AP Chemistry students, Spain Park. This is going to be a quick tutorial on Coulomb's law and compared and using it to determine the relative strengths of lattice energy, the energy needed to break ions apart. So, this is also going to help you on the couple of AP practice problems that you have to do for today. So, whenever an ionic compound such as NaCl, whenever it dissolves in water, the ions have to break apart, okay? And we've talked about that, the solute, solvent, and then the solute, and solvent, and solute, solvent, okay? And so we talk about the lattice energy. The energy, that's the energy needed to break the ionic bond, okay? So the bond type is ionic, but the energy needed to break that bond is called the lattice energy, okay? Now, anytime you have two charged particles, we have an Na plus surrounded by a Cl minus surrounded by an Na plus. And it just goes on and on and on, billions and billions and billions of these. But the actual ionic bond is the electron, the electric charge, the positive to negative attraction. Coulomb's law measures the strength of that attraction. Now the lattice energy, I'm going to let it represent the delta H of dissociation. Okay? That's really what is going to be our lattice energy. Because remember, when ions dissolve, they dissociate from one another. So delta H of dissociation, which I'm going to write just always as delta H dis, okay? That's going to equal the energy that needs to go in to break, to cause the ions to dissociate. That's going to be our lattice energy. And Coulomb's law says that that energy for any charged particles, it's anything positive attracted to negative, electron to the proton, any positive, even as the attraction, you rub a balloon on your shirt and it sticks to your shirt, the positive to negative, it's measured by Coulomb's law, okay? Which says that there's some constant K times Q1 times Q2 divided by R. K is a constant. You don't need to worry about it. It varies. Q1 is equal to the charge on the positive ion. Q2 is the charge on the negative ion. And R is equal to the distance between ions. Okay? So we have this. Now we're never going to really plug in real numbers on this. But we know the charges of ions. Group 1 is going to be +1, group 2 is +2, the aluminum family is +3, oxygen family is -2, halogens are -1. So that's what we put in for Q1 and Q2. What's the charge on the ion? R, the distance, we're going to use periodic trends. So we know that atoms and ions get bigger as you move down in the family. They get smaller left to right. Okay?
Testing is over for today.
So, Q1, Q2 are the charges, R is the size. So if I want to compare the lattice energy, if I want to say which one's going to have greater lattice energy, MgCl2 or MgBr2. Okay, which has the greater lattice energy? That's my question. Okay, I'm going to write it better. Okay, MgCl2 or MgBr2. Okay, so I'm going to look and I'm going to say the product of the charges. Well, I know that magnesium is +2, well, we'll say 2+, and chloride is -1. Now it's just -1 because we're going to be looking at Mg2+ attracted to a Cl- attracted to a Cl minus. So the lattice energy is measuring how much does it take to break those two apart. Okay? How much does it take to break the magnesium 2 plus from the Cl minus? So when I plug in, this is a +2 and a -1. So I'm here, I'd be +2 -1. Now we're just going to take the absolute value because we know the charge K actually takes care of the charge. Okay? And a negative is going to mean it's going to be an attraction. A positive means it's going to be a repulsion. But we have the Q1 and Q2. So magnesium here is 2 plus, bromide is -1. So the product of the charges are exactly the same. So the only thing that's going to change the lattice energy is the size of the ions. Well, we know bromine is bigger than chlorine. Therefore, the distance between here, when I do MgBr minus, this distance is going to be bigger than this one just because this electron cloud is going to be bigger. And as R gets bigger, delta H gets smaller. And that makes sense. The farther apart things are, the less attracted they're going to be. Long distance relationships are hard to maintain because the farther apart you are, the less bond there is holding you together. And so the bigger the radius, and we just use periodic trends. Now, if I wanted to do the same thing, but compare, let's say I want to compare LIBR to, well, let's say LIF to BEO. Okay? Now this one is going to be +1, this is -1, this is +2, -2. So if I look at the product of the charges, this is going to be 1, this is going to be 4 when I do Q1 times Q2. 4 is obviously way bigger than 1. I don't even worry about the size then because you look at product of the charges first. So if a +2 and a -2, they're going to be much stronger, much more strongly attracted to one another than a +1 and a -1. So this is going to have a greater lattice energy, which means it's going to take more energy to break them apart. They're going to have higher melting points because it's going to take more energy to break them apart. Okay? And so even the attraction when we have our Na plus and Cl minus surrounding it, when the water comes in to attract right here, this dipole to ion attraction right here, this is a Coulombic attraction. And so we can measure this. So again, the same thing, the greater the charge here, the more attracted the water is going to be to it. The smaller it is, the greater the water is going to be attracted. So that energy of hydration is also going to be dependent upon that Coulombic attraction there. So it's all any attraction between positive and negative. We don't plug in real numbers, we just plug in the charges and the size. If the charges are the same, you look at the size. If the charges are different, whichever one's got the greatest product of the charges, again, we take in the absolute value as we multiply these things times one another. Okay, we don't worry about the sign because we just want to see the bigger the charge difference, okay, the stronger the ionic bond is going to be. So that's Coulomb's law. So anytime you're talking about an ionic compound and how much energy it takes to break it apart, dissociate it, to melt it, you're going to apply Coulomb's law to measure the lattice energy. And it's just the product of the charges divided by the size, and we use periodic trends for that. All right? So that should help you to be able to answer those questions. And again, on 2016, remember, you do not have to do part A on that one because that's dealing with calculating the actual energy, and we're going to do that in chapter 5 when we study thermochemistry. All right, hope you're having a great day. Hope this helps.